Welcome everyone to the Graduate Online Combinatorics Colloquium. Today we have Foster Tom talking about a combinatorial Schur expansion of triangle-free horizontal strip LLT polynomials. Before he starts, I just want to remind everyone of our community statement. We have sort of three guiding principles at the Graduate Online Combinatorics Colloquium. These are that everyone is learning, everyone has something to contribute, and no one has all the answers. So these are fleshed out in the community statement on our website, but basically want to encourage you to ask questions either in the chat or by unmuting yourself and asking Foster directly, and to be patient with each other and sort of remember our core guiding principles. Okay, without further ado, Foster, take it away.
Great, thank you, Galen, for introducing me and for all the organizers for having me here. I'm very excited to tell you about my work last year about a combinatorial Schur expansion of these certain LLT polynomials. And I guess I'll also just say I'm keeping an eye on the chat, so feel free to ask questions there. Okay, so LLT polynomials get their name from Lascaux, Leclerc, and Thibon, who originally defined them in terms of ribbon tableau. But I'll be working more with this alternative definition by Haglund, Heyman, Laurer, Remmel, and Ulyanov that's in terms of tuples of skew diagrams. And just to make things a bit easier, I'm going to focus on the case where all of the skew diagrams are rows. There are still lots of interesting and difficult problems. So let me just start by describing what an LLT polynomial is with this definition. So if I have a sequence of rows, the horizontal strip LLT polynomial is going to be a generating function for semi-standard Young tableau on the sequence of rows. And I'm going to have a variable q that keeps track of inversions. What an inversion is a pair of cells that are either in the same column with the bigger one below the smaller one, or a pair of cells in adjacent columns where the bigger one is above and just one space to the left. So I'll show you an example of what this looks like just to help understand the definition. So yeah, here's an example. My lambda is this tuple of 3 skew diagrams, all of which are rows. The semi-standard Young tableau just means I need to fill all of the cells with positive integers so that they're weakly increasing from left to right. There are many, many ways to do this, but I've just written 2 of them here, t and u. I've just filled these with positive integers. And then for each one, I'm going to count the inversions. So inversions are either a pair of cells where they're in the same column and the bigger one is below. So in T, I've got 4 inversions like that. Or it's a pair of cells where the bigger one is above and one space to the left. So this 2 and this 1 make an inversion. So this tableau T has 5 inversions, and it contributes the term with the q to the 5, and then with a monomial of x's that just keep track of the entries that are used. So there are 3 1s. I have an x1 cubed, there are 2 2s, and there are 4 3s. So the tableau T contributes this monomial, and this is just one of many, many monomials in the LLT polynomial. Similarly, the tableau U, if I just find the inversion, so a bigger cell below a smaller one in the same column, and also a bigger one above and directly to the left of a smaller one. So I think this tableau U should have 3 inversions, and it contributes this monomial. Okay, so the LLT polynomial G lambda is going to be a sum of many, many terms that look like this. Are there any questions about, these terms or inversions?
Foster, sorry, I missed it. What was the power of Q from again?
The power of Q is the number of inversions.
Okay.
And that's just a pair of cells that I've drawn here in red.
Okay, got it.
Okay, great. So incidentally, if we were to express the LLT polynomial in the basis of Schur functions, I've just written down what it is here. If you don't know too much about Schur functions, they're generating functions for semi-standard Tableau. And I'll just say that because of representation theory and algebraic geometry, it's the problem that is frequently asked how to express a symmetric function in terms of Schur functions. So just for the sake of it, I've written it out here. So Lascaux, Leclerc, and Thibon originally showed that their definition of the LLT polynomial is a symmetric function. And then 10 years later, Gronowski and Heyman showed that LLT polynomials are in fact Schur positive. So all this means is that when written in the basis of Schur functions, the coefficients are polynomials of Q with positive coefficients. And this is a great property because of implications in representation theory and algebraic geometry. And I guess I'll just mention that Gronowski and Heyman used some very complicated machinery called Kazhdan-Lustig theory. And it's an open problem to find a combinatorial interpretation of the coefficients that arise. So that's a major question that I'll be looking into a little bit today.
I have a question just on this. Looks a little different than what I'm used to. It's strange to me that you have these separate pieces that all kind of go together. Like when I think of a young Tableau, I usually think of one connected thing. So is this still like a Tableau when you have these different pieces coming together, or is it something a little different?
Right. So LLT polynomials are indexed by tuples of skew diagrams. And I guess the generating function is over tuples of semi-standard Young Tableau.
Okay, yeah, I think I missed the tuples part, so that does make more sense.
If I just had a single shape, then it would just be a Schur function. I guess I wouldn't be able to have any inversions.
Oh, yeah, of course. Okay.
And maybe I'll just mention that if Q were equal to 1, then it's a product of the corresponding Schur functions. Just maybe that'll give you some more context.
Yeah, that makes a lot of sense. Thanks.
Okay, but great. Thank you for the question. So I'm just going to briefly mention some applications that LLT polynomials have in some other areas of algebraic combinatorics. If you're not too familiar with them, then don't worry, they won't really come up more in this talk, but just to provide a bit of context. So the shuffle conjecture was
before you say
recently
something
proven by Carlson and Mallet. And what it does is it gives
Okay, yeah, it seems like there's some technical difficulties. But hopefully we can, Faust, are you back? Yeah, we lost you
yeah,
for a second. We can go back to
I
it.
thought this was possible. So
Yeah, no
this
worries.
is something that might happen. Are we all good now? Okay, great. Sorry about that. So the shuffle conjecture was recently proven by Carlson and Mallet, and it gives a combinatorial interpretation of this operation nabla of an elementary symmetric function. It's significant because it gives a formula for the Frobenius series of the space of diagonal harmonics, which if you happen to have heard of the n+1 to the n-1 conjecture, that's the space of that dimension, proved by Mark Heyman. But this shuffle conjecture gives a combinatorial interpretation of this quantity, you sum over dict paths, and then next to each north step, you write a positive integer so that they're strictly diagonal inversions. I just want to say that this quantity in blue is exactly just an LLT polynomial indexed by a sequence of columns. So if you've heard of this shuffle conjecture, it can be seen as an expansion into LLT polynomials. The other thing I'll just quickly mention are McDonald polynomials. So McDonald space called Garcia-Heyman modules. If you've heard of the n factorial conjecture, Mark Heyman proved that these spaces have dimension n factorial. Haglund, Heyman, and lower. So I think these are called dict paths. Galen asks if these objects have a name. So I guess they just call those dict paths, but they call these entries word parking functions. Okay, great, thank you. So McDonald polynomials give the Frobenius series of these Garcia-Heyman modules. Haglund, Heyman, and Lower found a combinatorial expansion of McDonald polynomials into monomials. And they found that it implies this positive expansion in terms of LLT polynomials. So given a partition mu, you look at the cells that are not in the first row, and for every subset of those, you get a term involving an LLT polynomial. In fact, McDonald polynomials are known to be Schur positive just because LLT polynomials are known to be Schur positive. But I think it's only known that they're Schur positive via the expansion into LLT polynomials. So if we understand LLT polynomials a bit more combinatorially, then it'll tell us more about McDonald polynomials. Okay, so let me show you a bit about what's known regarding Schur function expansions. So Gronowski and Heyman showed that if I have a tuple of rows and they're all left justified, then an LLT polynomial actually coincides with another thing called a modified Hall-Littlewood polynomial. And it's well known that these have a very nice combinatorial Schur expansion in terms of a statistic called co-charge. So it's a bit complicated to define co-charge explicitly. I'll just maybe show you this. I won't really go into it. I'm just showing you this in case anyone's interested. But co-charge can be defined in terms of Schur de Turcan or in terms of some other things in terms of the reading word of a tableau. I think it's enough for me to just say that, oh, so there's a question. Is this also true for other non-skew shapes? So this bit here that an LLT polynomial equals this modified Hall-Littlewood polynomial. This is true whenever the rows are nested. So I'm going to say if the rows look something like this, then this is true. The LLT polynomial for the tuple of rows will be this Hall-Littlewood polynomial. I guess I'm saying something a bit more specific just to, just because it's a bit easier to state. But in a situation like this, this will hold. Thanks for the question. So I've written out some properties that are sufficient to define co-charge in case anyone's interested. But I'd say that I'm happy if the extent to which you understand it is co-charge is a number associated to tableau, and it's bigger if you've got lots of numbers on top of other numbers. I think that's probably enough for us to understand about it. In particular, this example here I think is sort of useful. If I happen to have a tableau with only two different entries, only i's and j's, then co-charge is just the number of entries on the second row. So in this case, co-charge would be 4. I think this gives us a bit of an idea of what I mean when I say co-charge measures how much there are numbers on top of other numbers. But now to see this statement in action, if I have this tuple of rows, so they're sort of left justified for 3 and 2, then to find the Schur expansion, if I want the coefficient of S621, for example, then I'll just find the tableau of shape 621 and of weight 432, so 4 ones. Oh, okay, so that, I guess that should be a 2 and a 3. 4 ones, 3 2s, and 2 3s. Then I'll just calculate the co-charge of these tableau, and it gives me the coefficient of this Schur function. So I guess what I want to say is that in the case that the rows are all left justified, there's a beautiful statistic called co-charge that explains this whole story very elegantly. And so the way I see it going forward is what I would like to do is find a generalization of co-charge that will give me the Schur expansion of an LLT polynomial, even when the rows are not nested in this nice way. So now I'd like to tell you about a couple of very recent results that are of this sort. So I guess the first one is that if my shape lambda consisting of rows is unicellular, which means that all of the rows have only one box, then we can associate a Dick path and a graph to this shape. And these authors, Schur, Nam, and Yu, found that if the graph takes on a particular form, they defined a statistic that gives the Schur expansion of an LLT polynomial. So I'll just try to show you what their theorem looks like in an example. Okay, so I know there's a lot to take in here, but we'll go through it slowly. So if I have the shape lambda, which I've drawn here, it consists of rows, and every row is just a single box. The way that we can get a graph from this is I'm going to number the boxes going in this direction. So from left to right and then from bottom to top along each column. And what we're going to do is draw a graph where the vertices are the boxes and where I have an edge between two vertices if it's possible to form an inversion between cells in those boxes. So I guess what I'm saying here is that the cells in these two boxes could form an inversion, and similarly between these and so on. So I form this graph gamma. I can also draw a Dick path, and the way I do that is that if these are, rows 1, 2, 3, and 4, the Dick path goes just above the cells that correspond to these edges. So my graph has 4 edges, 1, 2, 1, 3, 2, 3, and 3, 4. And so I get a Dick path that goes just above those boxes. This A here is the area sequence of the Dick path. So in each row, I just read how many boxes are between the path and the diagonal. So I've got 1 box, and then 2 boxes, and then 1 box. So this is the area sequence. And what Schur, Nam, and Yu showed is that if the graph gamma is a melting lollipop, I think this is really cute. So a lollipop is if we've got a complete graph and then the path coming off of it. And then a melting lollipop is if we maybe remove some of the edges, connecting this vertex to the other ones in the complete graph. So this is a lollipop graph. And they showed that in this case, we get a Schur. We get this formula for the Schur expansion. So what we do is, if I want the coefficient of S22, for example, I draw all of the standard Young tableau of shape 2, 2. I look at the descent set. So I is a descent if I plus 1 is somewhere above I. And I add up those indices of the area vector. So for S, I get a sub 2, which is 2. And for T, I get a sub 1 plus a sub 3, which is also 2. Martin Ruby asks, can one characterize the graphs which occur from lambda in this way? So graphs that look like this? This is a great question. The answer is yes. These are called unit interval graphs. So a unit interval graph just means a graph that arises from unit intervals of the real line, and where two vertices are adjacent if the intervals overlap. Unit interval graphs. So an equivalent characterization is that we can label the vertices from 1 to n such that if j is between I and k, then I adjacent to k implies I is adjacent to j and j is adjacent to k. And there's also another characterization in terms of forbidden induced subgraphs. So a unit interval graph isn't allowed to have an induced cycle of length at least 4 and like 3 other things. So yeah, that's a great question. The graphs that arise in this way are called unit interval graphs, and they have a few equivalent characterizations. Okay, so I just wanted to describe what Hernam and Yu did, because this is the sort of thing that I would like to do if I'm given a tuple of rows lambda, and maybe I'll write some conditions on what I want it to look like. Then I'd like to define some sort of quantity associated to tableau that will give me a combinatorial Schur expansion. Let me also just mention another recent result just a couple of years ago by Alexanderson and Ullin. They found a generalization of cocharge that gives a combinatorial Schur expansion of an LLT polynomial. I won't go into detail about what their cocharge is, but I'll just show you the kind of lambda for which their theorem applies. So if I have a skew shape here, I've sort of written it in French notation, so from top to bottom. If no column has more than 2 cells, then what they sort of do is I'm kind of detaching the rows from each other and getting this shape lambda here. And I just want to say that their theorem gives a formula for lambda that are of this form. So that's also exactly the kind of thing I'd like to do, find a generalization of cocharge that gives a formula for lambda that maybe looks something like this, or as general as I can make it. Are there any questions about some of these recent results?
Sorry, Foster, can you remind us why that generalization was important?
Oh, I guess this here?
Yeah.
Oh yeah, I guess I'll just say that LLT polynomials show up in a few areas of algebraic combinatorics. They're known to be Schur positive, and we'd really like to find a combinatorial explanation. The classical idea of cocharge applies when the rows are either nested or, I guess I could say, left justified like this. But we'd really like to be able to generalize it to just any tuple of rows. And this theorem is a result in this direction, that if the rows kind of look like a skew shape like this,
I see.
then they give a formula. And if we can make it even more general, then that would be even better.
Sounds good. Thanks.
Okay. Yeah, thank you. So yeah, maybe I'll start telling you about how I approached this problem. So I guess last year I was just happy to read the definition and play around. And one of the first things I realize is that if I have some cell X and some other row, then X makes at most one inversion with the cells in this row. So in either of these configurations that I've drawn here, the cell X can make an inversion with Y or Z, but not with both of them. So just to remind you how inversions were defined, I get an inversion between X and Y exactly when Y is bigger than X. And I get an inversion between X and Z exactly when X is bigger than Z. But because Y is to the left of Z in the same row, the definition of a semi-standard Young tableau tells us that Y has to be at most Z. So in the configuration, both of them, and the same on the right. So more generally, if I have two rows, I decided to think about the maximum number of inversions that I could have. Since a cell can make an inversion with at most one thing from each row, the most inversions I could get, I couldn't use a cell twice. So here on the left, I could get two inversions, but I can't get any more because no cell can occur twice in an inversion. So I was really interested in this number. On the right-hand side, when I've switched to R and R prime, I can get three inversions going like this. But that's the maximum number that I can get. So I decided to define this quantity m of r comma r prime to just be the maximum number of inversions that I could get between cells in rows r and r prime. I think that this pictorial description hopefully should be sufficient, but just to define it properly, I've written out exactly what happens. Are there any questions about how the maximum number of inversions is 2 in this case and 3 in this case? Okay, so great. What I wanted to do was I wanted to kind of generalize this unit interval graph idea, but instead of just having edges between cells that can make inversions, I wanted to measure how many inversions the rows could make. Oh, yeah, Galen asks about what I mean here. So I guess if I wanted to say exactly how I got this 2 and this 3, I can, on the left, I can kind of overlay it and see how many cells the two rows overlap in. But on the right, because of this thing where, I can make an inversion with the cell that's one column to the right, what I'm really doing in this case is I'm moving it over to the right and then seeing how many cells they overlap in. So that's how I got the 3. Okay, yeah, thanks for helping me clarify this. What I want to do now is if I have a tuple of rows, what I want to do this time is define a weighted graph that kind of keeps track of how much these rows intersect with each other, how many inversions I can make between rows. So I'll show you what this looks like in this example. On the left, I've got this tuple of rows. So I've got 3 rows here. What I'm going to do is focus on the rightmost cell of each row. And I'm going to label them going in this direction. So just as before, so I guess this is 1, 2, and 3. Now for each row, I'm going to draw a vertex of the graph. So I'm going to have 3 vertices, v1, v2, and v3, corresponding to the rows of my graph, or to the rows of lambda. For each vertex, I'm going to give it a weight that tells us how many cells are in the corresponding row. So v1 has weight 2, v2 has weight 4, and v3 has weight 3. And then I'm also going to weight the edges. So then the weight of the edge between V1 and V2 is just going to be this quantity here that tells me the maximum number of inversions I can get between the rows labeled 1 and 2. So between these rows, I can get 2 inversions. Between the ones labeled 1 and 3, I can get 1 inversion, and that gives me this 1 here. And between these rows labeled 2 and 3, I can get 2 inversions, and that gives me this 2 here. Yeah, so are there any questions about how I went from lambda to this weighted graph pi of lambda? Martin Ruby asks if it's a directed graph. I'm just thinking of it as an undirected graph, but the weights and the vertices both have edges. I really just want to keep track of the number of inversions I can get between pairs of rows. I guess I'm not really thinking about whether the cells in any row would be bigger than the cells in the other. Okay. Yeah, I think I've seen even this graph here, sometimes described as directed, where the edges just go from the smaller number to the bigger number. Yeah, I suppose I could think of it as a directed graph, but I'm not sure it's really come up. But yeah, thank you for the comment. So now that we have this weighted graph pi, I can state the main theorem that I came up with. So if I have a tuple of rows lambda such that this weighted graph has no triangles, then what I was able to do was define a generalization of cocharge that actually gives me a combinatorial Schur expansion of the LLT polynomial. So coming up, I'll tell you a bit about the methods and about what this generalization of cocharge looks like. But this is the idea. Whenever this graph has no triangles, I get the combinatorial Schur expansion.
And this graph has a triangle because it is a triangle, right? So that it wouldn't work for this?
Right, yeah, so it wouldn't work in this case. But yeah, whenever the graph has no triangles, I get a statement. And what I've been working on for the last little while is trying to work on the triangle case.
So if you get the triangle case, does that mean that you have a characterization for everything?
Well, yeah, I'm hoping to work toward that. I guess I need to figure out triangles and how they would fit together with the parts that are not triangles.
Oh, sorry. What I was saying is, I think earlier you mentioned one of the interval. I'm trying to make sure that I understand. So the interval order graphs couldn't have 4 cycles. So are these pi of lambdas then? They have similar rules that tell you
Oh yeah, this is a good question. So I haven't, yeah, I haven't mentioned it, but these graphs pi of lambda, only certain ones can appear. These are just interval graphs. So now they kind of correspond to intervals of the real line, but not necessarily of unit length anymore. They have a few characterizations. So if I is adjacent to k and j is between them, then j has to be adjacent to k, which is a little bit weaker than for interval graphs. And they also have a characterization in terms of forbidden induced subgraphs. So once again, I can't have a cycle of length bigger than or equal to 4. And I also can't have a couple of other things, such as this one. So there is a bit known about what kind of graphs can arise from this procedure. Although since I've introduced these weights, it's not very easy for me to say, given a graph that looks like this, whether it is actually admissible from a tuple of rows lambda. If
Foster, just to let you know, I think it just crashed for a second after you're done with the question, so I didn't really hear anything after that.
Oh, yeah, it said I had an internet problem, so I just paused a bit. But
Okay.
we're good now?
Yep.
Okay, sorry about this. So two tuples of skew shapes are called LLT equivalent. If not only they have the same corresponding LLT polynomial, but if I can kind of append some other rows to both shapes, and they will still have the same LLT polynomial. So if for any additional shapes new, I can just append them to both, and they'll have the same LLT polynomial. And more generally, if I have a linear combination of shapes, I can say that they're LLT equivalent if the corresponding combination of LLT polynomials is the same. And even if I append some additional shapes, they're still the same. This might look a little complicated, but I'll just show you in an example the kind of thing that I'm describing here. So I claim that these expressions in blue are LLT equivalent. What this means is that q times this LLT polynomial plus this LLT polynomial gives you this thing on the right-hand side. If we were to prove it, really all I need to do is show you a bijection between tableaux that are either of this shape or this shape, and tableaux that are of this shape or this shape, such that it preserves weight and inversions and such. And really the map is just given here in a few different cases. Maybe the only thing I'll really mention is that this tableau has one inversion and this tableau has 0, and the factor of q just does exactly what I want it to do for that. When I defined LLT equivalence, I actually promised a little bit more than saying the corresponding things were equal. I also sort of promised that if I add in additional shapes, the LLT polynomials are still equal. But what that comes down to is that the bijection here preserves the set of entries along each column, and so any additional inversions that you would make are also preserved. But the idea with LLT equivalence is that I can get a linear relationship between LLT polynomials corresponding to some different shapes. And I have a couple of results of that sort that allow me to manipulate LLT polynomials. So this next one, I say that 2 rows commute if this quantity, the maximum number of inversions I can make, is the same even if I switch the 2 rows. So on the left-hand side, I have 0 inversions between these rows. And on the right-hand side, I can get 3 inversions like this. Whereas if I switch the 2 rows, I could still get 3 inversions. But in the middle, I say that the rows do not commute because when the rows are arranged like this, I can get a maximum of 2 inversions. Whereas if I were to switch the 2 rows, then I would be able to get 3 inversions. So I felt like this concept in terms of the maximum number of inversions would be a useful thing to look at. And the reason I'm calling it commuting is because of this lemma about LLT equivalence. Essentially what it means is that if I have a bunch of rows, so if I have a tuple of many rows here, and if 2 rows commute like these 2 rows do, then I can just switch the 2 rows and the LLT polynomial will be the same. So that's why I'm calling it commuting. If I have a tuple of rows and 2 rows commute, I can switch them and get the same LLT polynomial. I also proved that if rows do not commute, then I can still switch them, but it's sort of up to a factor of q and a bit of a correction term. So I proved that we have LLT equivalence relations that look like this. But really, the point of all of this is that I can express a recurrence of LLT polynomials in terms of these weighted graphs. So I can say something a bit more general than this, but if my vertex v1 is adjacent to only one other vertex, then I can write down a recurrence that looks like this. So what I'd like to do now is to just describe how I came up with this generalization of co-charge and give you a bit of an idea and some examples of what that looks like. I guess one example that I sort of worked out early on is that if my shape only has 2 rows, so my graph just has 2 vertices and 1 edge, then the LLT polynomial actually takes on a pretty nice form. So I'll show you in an example what that looks like. For this 153 here, I have these terms S8, S71, and so on. And the power of q just goes up by 1 each time. But I told you that this number here is the maximum number of inversions. In other words, the maximum power of q. And if that number is smaller, what happens is that it just goes until it reaches the maximum value, and then it stays there. So it goes q to the 0, q to the 1, q squared, q squared. In this example, it goes q to the 0, q to the 1, and then it stays there. And it made me think that maybe what I should do is for each edge, for each I and j, I want to think about some sort of co-charge that tells me the contribution of having j's above i's in the tableau. And then what I want to do is take some sort of minimum between that quantity and the weight of the edge between I and j. So I guess I'll say co-charge is a statistic on Tableau that sort of loosely tells you how much there are bigger numbers above smaller numbers. And I wanted to define something that describes how much there are j's above i's. And I felt like looking at this quantity would give an idea of a way to generalize co-charge. In the case that my graph is a path, this was exactly the thing to do. So I wanted to describe some sort of thing that tells me the contribution to co-charge because of I plus 1s being above i's. And the way to do that was I define t restricted to i's and I plus 1s to be, I take my tableau, I only look at the i's and I plus 1s, so I get a skew tableau. And then there's this process called rectifying that will just give me a straight shape tableau. And I mentioned that if I have a tableau with only 2 different entries, the normal definition of co-charge is just the number of entries on the second row. And it turned out that this was exactly the right thing to do. So if I have a weighted graph that's a path, then doing this gives me a generalization of co-charge that gives me the right Schur expansion of LLT polynomials. So maybe I'll just show you an example of what that looks like. If I have a tuple of rows such that the weighted graph is this path here, then if I want to calculate the coefficient of some Schur function, let's say S733, what I do is I look at all of the tableau of shape 733 and of weight 4324. So there are 3 tableau here. Maybe we'll focus on S. First, I just restrict S to and it has 2 entries on the second row.
Just to let you know, Faust, you cut out for like 20 seconds there.
Oh, okay. Yeah, thanks for letting me know. So I restrict S to 2s and 3s. There's an algorithm to slide the boxes and get this tableau, and it has 2 cells on the second row. And then I do the same with the 3s and 4s. I slide the boxes. There are 2 cells in the second row, but I need to take the minimum between that number and the weight of the edge between V3 and V4. So in this case, even though I've got 2 cells here, because that edge weight is only 1, I only get 1 for this. So I add those up and I get a co-charge of 4 for S. Similar thing for these other tableau, and it gives me the coefficient of this Schur function. So are there any questions about what this formula looks like? This to graphs with no triangles? So Galen kind of alluded to this earlier. Can we describe graphs that arise from this process? And not all graphs can arise. I might be a little bit dishonest in saying I did it for triangle-free graphs, because if a graph has no triangles, it actually takes on a bit of a specific form. There can't be any cycles at all, so it must be a union of trees. And in fact, they have to be what are called caterpillar graphs. I think this is so cute. A caterpillar graph is just a path with a few vertices joined to some of the parts of the path. So that's a caterpillar. And I guess now I tried to do a similar thing, but there are a couple of problems. So for example, I've got V2 adjacent to V4, and I need to decide what co-charge sub 2, 4 should be. What should it mean to restrict my tableau to 2s and 4s and look at this contribution? If I only look at the 2s and 4s, I don't get a skew tableau anymore, so there isn't a canonical way to rectify it. It turned out that I should restrict to entries between 2 and 4, but then this gave me another problem because I don't just have 2 entries anymore. So it turned out that what the right thing to do is a little bit weird. The way that we thought of co-charge before, if I just have 2 entries, is it's the number of entries on the second row, which in this example is 5. And a really weird way to think about this number 5 is, let me try to take this bottom row and move it to the left so that the entries are still strictly increasing from bottom to top. So I can move it twice, but not any more than that, because then I have a 2 on top of a 2. So instead of thinking about it as 5, I can think of it as the number of 1s here, which is 7, minus the distance that I could move the bottom row to the left, which is 2. And this is a really weird way to think of the number of entries on the second row. But when I generalized it to these other tableaux, this was exactly the right thing to do. So this is what f of t is, just the distance I can move left. I've written out the definition here, but essentially it's just this distance. And then t restricted to i's and j's. Oh, okay. Yeah, this is a bit unfortunate with the internet connection. I was just saying that in general, what I do is I restrict a tableau to entries between I and j and rectify it. And then this idea of co-charge sub I comma j is just the number of i's minus the distance I can move the bottom row left, which kind of agrees with this situation. And then that gives me a combinatorial Schur expansion of these LLT polynomials. I've got an example here. It's pretty similar to the last one. Maybe we can look at it later, but I'll just close by saying that what I've done was I've been able to express this LLT polynomial in terms of Schur functions, but the formula actually only uses this weighted graph rather than the rows themselves. So and there are no triangles, then they have the same LLT polynomial. I actually believe that this happens in general, and I guess something a bit more that the weighted graphs only need to be isomorphic. So I believe that I should be able to erase these labels and recover the LLT polynomial just from this picture. So I believe that the row lengths and these integers I was interested in should be enough to determine a horizontal strip LLT polynomial. Okay, sorry about the internet problem, but thank you for bearing with me and for your time and attention.
Let's give Foster a round of applause. Are there any questions from the audience? So I have maybe one small question as an outsider, which is, so I know that there's some stuff known about vertical strip LLT polynomials. So if your conjecture was true, could you combine it with known stuff to say something stronger?
Oh, okay, yeah, great. So vertical strip, vertical strip results and horizontal strip results are more or less equivalent because there's a formula in terms of if I conjugate all of the shapes, then I get q to some factor, and then something like this. And there's an omega somewhere. So Alexanderson and some others found some results about tuples of columns. They expanded them into elementary symmetric functions and did some things like that. I just preferred to work with rows instead of columns, but the results are all more or less equivalent.
Okay, cool. Other questions for Foster? Okay, great. If there aren't other questions, we will thank the speaker again. And I think Andres has an announcement.
I guess, yeah. So, well, we hope that you join us next week. So next week we'll have, we'll have Sophie Reberg from FU Berlin, and she'll be talking to us about, let me make sure that I get this right, combinatorial reciprocity theorems for generalized permutahedra, hypergraphs, and pruned inside-out polytopes. So if you're a fan of that stuff, please join us. And if you're not, well, you should still join us and you can become a fan. And also we're looking for organizers of the GOCC for next year. So if that also interests you, please reach out to the GOCC email and we'll keep a running list of people that are interested. As you may know, all 3 current organizers will be finishing, so we won't be graduate students. And so we'll be passing on the torch. So if you're interested in that, please join us. And if nothing else, let's thank Foster for being our first speaker of the spring semester.